in this lesson, we're going to dig into parallelograms, which are kind of like the grandfather of all the major quadrilaterals we're going to be looking at. The other day we did heights and trapezoids. They're kind of like cousins or something like that, but parallelograms are going to be the main focus, just like triangles was the main focus last time. Parallelograms are going to be the focus of Unit 4. So you'll be able to define a parallelogram and find an area. And like we mentioned in the last lesson, areas everywhere. Most common that I deal with would be whenever I paint a room. You have to figure out how much paint you need. You got to calculate the area of it. Ties into calculus when and if you ever get there. And then volume is also connected to area. So you can apply the properties. You know you get it when you can apply the properties, perform the arithmetic, and get the area of whatever the shape. So definition of parallelogram first. Two pairs of parallel sides. We talked about trapezoids the other day, where basically the two bases, the top and the bottom, are parallel. For parallelograms, the sides are also parallel. Top and the bottom are parallel, but also the two sides. And being parallel is going to lead us to a bunch of properties related to parallel lines, like interior angles, corresponding angles, same side interior angles, all that stuff. We can apply any of that because of the lines are parallel. So, first thing we're going to look at is, can we prove the two triangles are congruent? When you draw in one diagonal, does it split it into congruent triangles? So we're given that it's a parallelogram. So our reason, given. Then we're going to go on and say that the sides AB and CD are parallel, and so are AD and CB. That's what we just wrote down on the last page. That's the definition of a parallelogram. So now that we know parallel lines, we also have this line BD going down the middle. That's a transversal. That's a Z shape. So angle ABD is congruent to angle CDB, because those are, since it's the Z angles, that is alternate interior. We could actually do the same thing and get another pair too, the ADB and CBD. If you draw the Z this way. Kind of backwards, but it's still a Z. You still got parallel lines from the top and the bottom. So it gives you just different angles. So from the parallel lines, we got a bunch of congruent angles, the ones we just marked. And then one more thing, we always have that side right there, BD down the middle. That's because of the reflexive property. So looking at what we've marked, parallel lines helped us get angles. We erase those markings. you can see a little bit better is what we've got for triangles. On each triangle, we've got the two angles and the side in between. So that means the triangles are congruent. Two angles, the sides in between, ASA. So we got some parallelogram theorems. A lot of them we're going to get to. And they are all going to pretty much come back to the fact that when we draw in a diagonal, it makes two congruent triangles. Which means they're going to have corresponding parts that are congruent. So since those diagonals that we could draw in make congruent triangles, there's a lot of things we can talk about. First of which is going to be opposite sides are congruent. Because when we draw in that diagonal, you get two congruent triangles. This side's going to match up with that side. Corresponding parts of congruent triangles. CPC, TC. Same thing with the other sides. These two sides match up with those two sides. So opposite sides are congruent. No matter what. If it's a parallelogram, opposite sides are congruent. It's automatic. We also get opposite angles are congruent. Really for the same exact reason. Angle A right here is going to correspond with angle C. They're opposite each other. And if we drew in the other diagonal, split up the triangles the other way, we'd still get congruent triangles, and we would get those angles are congruent because they're corresponding. So opposite angles are congruent. We also get, this one's a little bit harder, diagonals bisect each other. The diagonals cut each other in half. So we haven't looked at a drawing yet that had both diagonals. But we're drawing both diagonals here. They intersect here in the middle, so we know we would get like vertical angles right here. We also know alternate interior angles, so what really happens here is this triangle on the left would be congruent to this triangle on the right. Marking them with the stars. Same thing here, this triangle on the top, that's supposed to be a different color. This triangle on the top is going to be congruent to that triangle on the bottom. The ones with the red stars in it are congruent, the ones with the green stars are congruent. It splits it into two different sets of congruent triangles, which means within those smaller triangles, those sides would match up and be congruent, and so would those sides. So the diagonals bisect each other. They cut each other in half. So three properties right away from parallelograms. Opposite sides are congruent, opposite angles are congruent, and diagonals bisect each other. So here's a parallelogram. We've got markings on the diagonals. That last property we just said stated that diagonals bisect each other. So those two sides are congruent, and those two pieces are congruent because diagonals bisect each other. So since diagonals bisect each other, we know that these sides are congruent. We can write equations. 5y minus 12 is going to be equal to y. And then from the other side, we can write 1/2 x plus 3 is equal to 3x minus 2. Because diagonals bisect each other. They're congruent. So we can solve these out. Get your y's together and solve. So minus 5y and divide. So you get y equals 4. Do the same thing, solve for x. Get your x's together. So we've got a fraction here. If you don't like fractions, get rid of them. You can get rid of the entire fraction by multiplying everything by 2. So you get 2 times 1/2 is just 1. That'll be 2 over 2 is 1. So distribute it. That 2 gets multiplied to everything. So 2 times 3 is 6. Multiply it again. 2 times 3x is 6x. 2 times 2 is 4. Now no more fractions. That'll be a little bit easier to solve. You can get your x's together. Move everything to the other side. So you get 5x is 10, so x is 2. Now, if this question said, or didn't say solve for the variables and said find the length of something, we would have to plug it back in. But it just said solve for the variables. But if it said find the length of AC, we have to plug it back in and find the length. Or if it said find the length of DB, yeah, plug them back in and find the length. Here we've got another parallelogram. This time we've got angles marked. We know that opposite angles are congruent. Since opposite angles are congruent, and we also know that this is a quadrilateral, it's got 4 sides. We know that all 4 angles add to 180. We also know that opposite angles are congruent. So that means we know that since this is 145, this is 145. We also know that B and D are going to be the same thing. B and D are going to be the same thing. A and C are going to be the same thing. Another way that we could apply this, which works out the same way here, if you think of that as a parallel line, and that as a parallel line, and here's a transversal, these 2 angles right there and there are same side interior, which means they're supplementary. They add up to 180. So if you don't want a big equation that uses all 4 angles, you don't need a big equation that uses 4 angles. You can have a smaller equation that just uses the 2. 145 plus 3x plus 8 equals 180. That's because those are parallelograms. So you got parallel lines cut by transversals. You can even add that as another property and say that consecutive angles are supplementary. So we can solve this out. Subtract the 145. you get 35. Subtract the 8. And then divide, you get x equals 9. You can do the exact same thing, solve for y over here because the consecutive angles are going to add to be 180. 6y minus 7 plus 145 equals 180. Add the 7. So you get 6y is 42, which means y is 6 times 7 is 42. 7. So x is 9, y is 7. Again, this question just said solve for the variables. It didn't say find the angle. So that's it. So here we've got another example. We've got some angles. We've also got some sides. You know that these opposite sides are congruent. That's a property of parallelograms. So 7y minus 4 equals 4y plus 11. So solve it out. You get 3y equals, let's add that 4 over. 3y is 15. So y is 5 because opposite sides are congruent. Now, the other piece of this, the other property, we know that these lines are parallel. And there's a transversal. So you get those z angles, which means they are congruent. Because they're alternate interiors. So there's another equation. 4x plus 1 equals 5x minus 13. There's a lot of ways to get equal parts. So subtract the 4x, you get x. Add the 13, you get 14. And you're done. X is 14, y is 5. For area of a parallelogram, it's just base times height. Now, the only trick is that the base and height must be perpendicular. Height goes straight up, just like when we were talking about the centers of a triangle. We said that the height has to go straight up. The altitude goes straight up. So we've got some coordinates. To find that area, I would suggest graphing out the points first so you can see everything. So we've got all 4 points plotted. There's our parallelogram. Now to find the area, we need to know the base and we need to know the height. The base is easy, we can count it. This side down here, from T to H, that's the base. It's 11 boxes wide, 11 units wide. And our height has to go straight up, like right here. That's our height. Since that's straight up, you can also count that out. It's 4. Our area, base times height, 11 times 4, 44 units squared. What are the coordinates where MT and AH intersect? So let's start kind of the same way. Let's plot our coordinates. Is that the same one? Same coordinates. So when we have all those plotted, this is M, A, T, and H. It says diagonal MT and diagonal AH. Where do they intersect? Well, if you've got a really good graph, you can draw it out really nicely. You can see that they intersect right there. If you didn't have a very good graph, it might be harder to see, but you can check it with algebra because we know that the diagonals bisect each other. It's one of our properties. Diagonals bisect each other, which means they're going to cross at the midpoints. They will always intersect at the midpoints. So we could find the midpoint of either one of those, MT or AH. Remember, midpoint is x plus x divided by 2, y plus y divided by 2. That's our midpoint formula. So if you're trying to find the midpoint of MT, M and T, you can take the x coordinates. -2 plus 6, and you're going to divide by 2. You can take the y coordinates, 1 and -3, divide by 2. Use midpoint formula to see where they intersect. So you're finding the midpoint of MT. So -2 plus 6 is 4, divided by 2 is 2. 1 minus 3 is -2, divided by 2 is -1. We got the same answer because it's the right answer. Could have done the midpoint of AH also, same way. 9 and -5 divided by 2. 1 and -3 divided by 2. You get the same answer. Same way. That's because the diagonals bisect each other. So here we've got one side and then another point. It's going to be part of that parallelogram. That point's going to be a vertex. So here's one side. That's going to be the other or another side. And we got to find out where C is going to belong. C is going to be over here somewhere. Now, since it's a parallelogram, the lines have to be parallel, which means that this side is going to be the exact same as the side down here. It's going to be the exact same as the side down here. So by doing that, you can see pretty easy where it's going to be. Now, Since you on your paper can't trace and then drag, your equivalent on paper is going to be to count. How much does it go up? How much does it go over? Think of it like a vector from way back in Unit 1. It goes up 1, 2, 3, 4, and it goes to the right 1, 2, 3, 4, 5, 6, 7. So it goes right 7, up 4, like a vector. So from K, we're going to go right 7 and up 4. Just like a vector. So that's where point C belongs. So we can figure that all out. But if you look at the question, it doesn't say what are the coordinates of C. It says what's the equation of the line that contains C and K. So if you have it all graphed out nice and neat, you can extend it, but that doesn't have a very nice y-intercept. Here's your x and y-axis. It doesn't have a very good y-intercept, so it's probably not going to be a very good y equals mx plus b equation. But we do know the slope, and we do know a point that it passes through. It has to pass through point K, which is the point 3, 3. 1, 2, 3, 1, 2, 3. And we know the slope because it has to be parallel to LU, which means it has to go up, rise over run, up 4 over 7. So you're writing an equation with a slope of 4/7 that goes through the point 3, 3. Y minus y1 equals m x minus x1. M is 4/7. Then you fill in x1 and y1. x1 is 3, y1 is 3. There's your equation. You can distribute that and convert it to slope-intercept form. We would just get fractions though, so I don't think it's needed.